All right. Yeah. So welcome everyone. So today is my great pleasure to have Dr. Jiahao Chen from JP Morgan AI Research to visit us virtually and speaking our department seminar. So Dr. Chen is AI Research Director at JP Morgan AI Research in New York City and leads research in responsible AI, building new capabilities for holistic reasoning about explainability, fairness, security, robustness, privacy, safety, and related concerns. So he was a professor, a senior manager of data science at Capital One, focused on machine learning research for credit analytics and retail operations. So when still in academia, Jiahao was a research scientist at MIT CS201 lab, where he co-founded and led the Julia lab, focusing on applications of the Julia programming language. So I believe many of you must have heard of Julia programming language. This is very useful programming language and has a lot of applications in data science, scientific computing, and machine learning. And Jiahao has published more than 40 papers and has authored over 120 packages for numerical computation, data science, and machine learning for Julia programming language, in addition to numerous contributions to the base language itself. And yeah, so actually both Jiahao and I graduated from the University of Illinois at Urbana-Champaign, and we met last year, and we feel very excited to know each other. All right, so please welcome, please join me in welcoming Jiahao to give the talk.
Thank you so much, Chen. So I'd like to add on to that by saying that I think we first connected on Twitter. So if you ever are told like social media didn't do the world any good, I think we have a counterexample here. So I'm very happy to be here. Yeah, so very happy to be here, and I'd like to keep this somewhat informal. So please feel free to write questions. I have the window open so we can kind of take it more interactively, and I would also like to have some audience participation. So I have a few questions along the way. So I'd like to get people's feedback and input on that as well. All right, so without further ado, first I need to tell you that this is not a investment presentation. And if you lose money because of this presentation, I am not responsible, and neither is my employer, JP Morgan. All right, so what JP Morgan AI Research does, so let me just start with that. So we have several core research areas in various aspects of artificial intelligence. And I work specifically in the area of secure and private AI and also safe human AI interaction. And for the various aspirational research goals, we're interested in solving the long-term problems of the financial industry using AI. These are obviously very ambitious goals, and we hope that through state-of-the-art research, we are able to make some progress towards solving these long-term problems in the industry and challenges. And so the question of establishing ethically and socially good AI is, of course, what I work on the most, and this is the topic that I'd like to speak with you about today. And we're a research unit at a bank, and it is it is like many other research institutions, primarily concerned with doing new research. So we also actively engage the wider research audience in the work that we do. We also give out PhD fellowships and faculty awards. And of course, we have full-time opportunities. So if anyone's interested in that, happy to talk about that. And please feel free to visit our external website, which is jpmorgan.com/AI, where you can see more details about what we're doing. All right, so when I first joined this company, I knew that JP Morgan was a large bank, but it didn't quite sink in how large this place was until I started looking at some of these key metrics. So this company employs over 270,000 people across the world, which is actually quite a staggering number if you think about it. It's like the size of a small city, and there are about 50,000 of us who work in technology in one way or another within JP Morgan. So this is in terms of like the size of in the people that we have, but also this number in the bottom left, the payments processed daily exceeds $5 trillion a day, and I really don't know how to think about this number until I was given this little bit of context, which is $5 trillion US is something like 60% of the world's dollar flow in the world. So if you send a US dollar from point A to point B in the banking system, chances are greater than even that JP Morgan processed the payment transaction at some point. So just think of the scale of real-time analytics problems that exist in this space as an example. So I'm here to tell you today really what is on the title. Why do we need fairness and explainability in financial services? Why are there actual research problems that are worth studying and publishing about? So here's one of the earliest little write-ups I did. So in the United States, consumers have the right to explanation. So if we make a credit decision, especially if it's not in the customer's favor, the bank must provide a reason, and they can't just say, no, we won't give you the loan. We have to give you a reason that you can understand. And it can't be because the model said so. All right, so in this example, here's a supervillain. She's applying for a credit card, and the bank said, no, we're not going to give it to you. So maybe I don't like the fact that you work as a supervillain in this example, but maybe there are other reasons you could give, and some of which could be business reasonable, like having not a stable income. Some of these are irrelevant. So for example, the fact that you drive an orange car, and some are illegal in the sense of being discriminatory, like saying, because you're a woman, I will not give you the credit card. So this is to give you some sense of the plurality of possible explanations that can be given to a consumer. The specifics of what are acceptable in terms of credit decisions depend a lot on the specific market or jurisdiction that you sit in, but most of them have some sort of fairness or explainability requirement as part of the regulations that we have to comply with in those markets. This is a fairly complex topic that I don't have time, unfortunately, to speak about in detail, nor am I really the person qualified to speak most about why there is a historical and present societal inequalities, especially when it comes to credit, mortgages, housing, and other aspects of the US economy. I would highly recommend that people who are interested in these topics have a look at these 4 books that I've read, and I think were particularly illustrative and very revealing about the complex economic and social history that got us to where we are today. So I'll just move on for the interest of time. And this is where I am going to do this experiment where I'm asking for people to vote. So let's say you're the bank now, and let's start with this warm-up one. So I have a policy that says I only give you the credit card if you are a man. All right, so how many people think this is fair? So if you think this is fair, please use the thumbs up. And if you don't agree, please use the astonished face emoji. Somebody wants to raise their hand? All right, yeah.
All right. I just click the raise hand button by mistake.
Okay, all right.
I think there's no such a function in our Zoom webinar, but
oh really? Okay.
Yeah.
Why don't people write in the chat as well? So please feel free to express yourselves in the chat, and we'll go from there. So I see some responses already. Yeah. All right. So hopefully this was really a warm up here, and yeah. All right. So this was a warm up to clearly say that like this is obviously unfair because we're making a decision on the basis of your membership in a protected feature. So how do we formalize this in US law? It falls under this legal notion of disparate treatment. So in the US, sex is a protected class as defined in one of the laws that govern credit decisions. And basically, disparate treatment is the explicit decisioning based on the on the protected class membership. So a policy like this is clearly not going to be allowed. And it's hopefully everyone agrees that this is not fair. Great, thank you. So let me give you a second version of this, which is if you live in zip code 02139, which happens to be the zip code for MIT in Cambridge, Massachusetts, we will give you the credit card. Otherwise, we won't give you the credit card. And I will point out that the zip code is not a protected class under US fair lending law. So I'll ask again, how many people think this is a fair policy? Please feel free to write in the chat what you think. Okay, it's unfair. Chen, do you want to kick us off by saying why you think it's unfair?
Yeah, I just think this kind of information might be irrelevant to the, for example, evaluation or decision making regarding someone's credit. So that's why I think it's unfair. I don't have any other specific reason. Yeah.
Okay. Yeah, I think that's definitely a reasonable point. So what does zip code have to do with creditworthiness anyway? That doesn't seem to be directly related to whether or not you'll be a good customer. Now, this is where the intersection of the economic history of this country comes into play, because there is this historical practice known as redlining that was explicitly decisioning based on whether or not you lived in a particular neighborhood or not. And so what you're seeing here on the left is an old map of the city of Philadelphia. And this was from a federal bank that issued mortgages. And what they decided to do in this picture is to literally color in red the neighborhoods that they think are risky and therefore you shouldn't give mortgages to. And the ones that in blue are the ones that we will approve, and the yellow ones are like, okay, like we're not sure. Now the thing that this correlates with, however, is also racial demographics in particular. And so what you're seeing on the right is the census data from 2010. So 80 years after the fact, you can still see the strong correlation between being a minority-majority neighborhood in Philadelphia and that correlating with being marked red on this map. Excuse me. So the short take-home message here is that zip code, although it is not a protected class like race, gender, or age, is however highly predictive of race, and therefore if you make a decision based on zip code, it's actually effectively equivalent to making a decision based on race, and therefore this is not allowed under the current laws as well. All right, so last one. So if you have a credit score that exceeds 670 points, I will give you the credit card. Otherwise, I won't give you the. What happened to the recording? But all right, thanks. So shall we also take a poll here? Like, how many people think this is fair or unfair, or maybe you're not sure? Okay, so some people are saying it's fair. Anyone wants to take the contrary view and say it's unfair? Right. Okay. All right. So it looks like more people are saying that this is fair. All right. So why is this a fair policy based on what we've discussed so far? All right. So it's clearly not falling afoul of the notion of disparate impact. Disparate treatment, which is what we talked about previously. There is no explicit or implicit dependency of the decision policy on race, sex, gender, age, or other prohibited features. However, there's this other notion of discrimination known as disparate impact. And this is defined as having a facially neutral policy that nonetheless results in a discriminatory outcome. So now the question here is, would this policy, which on the surface is racially neutral, gender neutral, age neutral, could this still result in a discriminatory outcome? So to dive into this a little bit more, why is 670 an interesting number? This is the official guide to what a credit score is from MyFICO, which is one of the most widely used providers of credit scores in the US. And you can see that the features that go into a credit score, about half of them have to do with some sort of payment history, length of credit history, and then the rest of it's like how much you're actually using and how much you're actually opening. And this number 670 is basically the unofficial borderline between good and not so good credit. So now, is there actually a correlation between credit score and race? And the answer turns out to be yes. There is actually a distributional difference that is measurable. So this particular set of graphs come from this study from the Federal Reserve. And so what you see here are for 3 different racial subgroups, Black, white, and Hispanic. We're seeing also for 3 different years, 2000 in gray, 2006 in black, and 2014 in red. And 660 is more or less where the cutoff was for good versus not so good credit. Now, what you see here is that Black and Hispanic seem to have a very different distribution from white. So whereas Black and Hispanic seem to be roughly centered around 620, 650-ish, and you see that distribution improves over time somewhat. You see that the white distribution is very heavily skewed towards the high end of the credit scale. And furthermore, that skew actually has increased over time. And so therefore, under this policy, you could argue that there could be disparate impact issues that we should be thinking about, even though the use of credit score is a facially neutral feature because of this implicit correlation. A slightly more nuanced problem here is the fact that missingness of credit score itself also depends on race. And so this is yet another study from the Federal Reserve that was published in 2016. And for the time being, let's ignore the difference between the different color codes. These are different kinds of people who don't have enough data, but all of the people here don't have enough data to compute a credit score. And this is probably something that many of us who came to the US to study here have experienced firsthand, that it's very, very hard to get the first credit card. But once you get the first credit card and establish that history, it's much easier to get better credit cards that have more generous credit limits and rewards and things like that. So what you see here on the right is how that percentage of missingness varies by race. And you see that Asian and whites have a similar rate of about 15 to 20%. And every other race in this study has a much higher rate of like 25 to almost 30%. And so even the ability to use a feature could itself have a correlation with a prohibited basis such as race. So I'm not going to answer the exact question that I posed because as you can see that there's some vagueness in the actual decision of whether or not this policy of decisioning based on one variable could be fair or unfair. So just to summarize where we are so far, there are fair lending laws in the United States that define protected classes, the 3 big ones being race, gender, and age, and we cannot make any decisions based on your membership in any of these classes. Secondly, there are actually 2 different and sometimes conflicting notions of discrimination that exist in US law. One is disparate treatment, which is roughly input fairness, and there's disparate impact, which is roughly outcome fairness. And the third thing is that even though you may not explicitly use protected class as a feature, what is called the proxy variable problem, basically other features that look neutral but actually can be highly predictive of a protected class, are also problems that we have to think about in the actual usage when we're designing and building models. All right, so I'm going to move a little bit faster here and just say this, I think, has been a really fruitful area of research personally for me, because just addressing all of these real world problems has led to some new results which we have not seen in the CS literature. So I will talk mainly about the first 2 classes of problems today. So first of all, the fact that we actually need to collect labels about customers in order to tell if we are discriminating against customers. But in some of these problems, we actually are not able to collect this information. So how can we test for discrimination when we don't know the protected class membership of our customers? This is one important problem that comes out in practice, especially for non-mortgage products, so credit cards, auto loans, and things like that. Secondly, how can we think about the trade-off between multiple notions of fairness? So we've already talked about how there's two different potentially conflicting notions of input fairness versus outcome fairness. So can we figure out what is there a tension between having both input fair and output fair models? And given that if we have such unfairness, how can we fix the model so that's no longer unfair? So I'll skip the last one for the interest of time. If there's any interest, we can talk about it later. All right, so the first paper that I wanted to talk about was published in the FatStar conference in 2019. These are my wonderful collaborators who have worked on this problem with me. And all right, so we've just talked about this. There's sort of an inherent contradiction in the way that we have to do compliance testing for financial products. So under fair lending laws, we can collect labels like race for mortgages, but we can't do that for other consumer loans such as credit cards. And if you think about it, like when you were applying for a credit card, if you've ever applied for one, we would never ask you what race you are, because it's a, you know, I think from a consumer perspective, it clearly looks like a strange question to ask. Like, why would you ask if you know you can't make a decision based on that? So if in practice we're not actually able to collect these labels, but yet we need to compute some metric of bias. So the contradiction here is, how do we do that when we don't know the labels? And so now we're looking at a method for imputation of labels. And can imputation give us a rigorous and robust estimate over here? All right, so I'm going to talk about one particular model that goes by the name of Bayesian improved surname geocoding. This is a fancy way to say that we guess your race based on where you are and your last name. So in this example, this caricature of California, there are 10 Smiths, and these are the distributions by race. So basically, what I would do is compute this conditional probability of being in a race, given that your name is Smith and you live in California. And so, based on the demographics of this neighborhood that we're looking at, we would basically just compute the population ratios as the answers to this conditional probability. So the second thing about BISG is that it applies a threshold to try to convert the actual probabilities into a true label. So what we're saying here is that we apply a threshold of 65%. So if more than 65% of Smiths in California are white, then we basically assume that if you are a Smith in California, that you are white. This is basically the imputation rule that we are using. One obvious thing that we will notice right away is that 30% of people get misclassified under this imputation rule. And so now the question is this misclassification error a problem in actually doing the estimation? So you might imagine that it's because it's based on the threshold, all I have to do is just crank up the threshold. But now that there's a different problem, which is that if you have a distribution of race in the neighborhood that doesn't meet the threshold, we can't impute it. So what do? So either you need a different rule for imputation, like a lower threshold, or you just have to exclude this neighborhood from the analysis. And so if you crank up the ratio to 85% now, you would go back to the Smith in California example. You can't impute the race based on this rule, and therefore you discard this neighborhood from the analysis. So what this means in practice is that if you choose a high threshold to compute an imputation, you get better classification accuracy in predicting the labels, but you also result in higher sample loss when you're actually computing the fairness metric downstream. All right. So you may think this is a very naive approach. Clearly, surely people are not doing this in practice, but it turns out that they are. So there was a fairly famous case back in 2013 when one of the government regulators fined a bank for discriminatory auto loan pricing. But the problem here is that that people pointed out was that in auto loans, you don't collect these labels. So how on earth could you know that you had some sort of discrimination against race, gender, or age? And then it turned out that they had to publicly disclose the fact that they were using this sort of what they call a proxy model for identifying race and ethnicity of customers based on public information such as name and location in the census data. So this had a bit of a blow up in the news at the time. So there were questions of whether or not this methodology itself was biased, or maybe it was like erroneous in various ways, and there were all sorts of congressional hearings and things like that. One of the so I'll point people to this to the first reference here if people are interested in a specific case. So these consultants did a comprehensive evaluation of the actual case involved, and they came up with this empirical finding that that actually using this imputation rule overestimates the outcome disparity. So it in general thinks that you are more unfair than you actually are. And that was actually one of the main findings from the technical point of view as to what exactly the controversy was around. And so the research question here is, why does it overestimate? And is it ever possible to have the converse happen? So here's the research question that we set out to ask, which is take one of the simplest notions of unfairness, which is demographic disparity. So we basically compute the average loan acceptance rate, which is the outcome. So we compute its average for the advantage group, and then we subtract that from the same thing condition on being in the disadvantage group. And so now we take this as the quantity that we're interested in computing, but we don't have the actual labels. So now what do? We basically take the true labels of membership and replace them with imputed labels of membership. So the main result of this paper is that the estimation error actually can be factored into two different sources. And I'm just giving you the cartoon illustration of what they look like. So one is inter-geolocation variation, which occurs when the outcome variable, which is the loan decision, the actual feature of relevance, which is the income, and the demographics are all perfectly correlated. So in this example, there's a high income neighborhood that is majority advantaged, and also majority therefore classified as the advantage group. And everyone in this neighborhood got a loan. And the exact opposite is true in a different neighborhood. It's low income, majority minority group, and therefore everyone is classified as disadvantaged and nobody got the loan. So under this setup, you would compute now that the true disparity, the true disparity, if you count how many people across both neighborhoods got the loan, and you basically do the difference based on the race groups, you would see that in this example, you should end up with 5, but actually the estimated disparity that you get is 9. So you would think that everyone in this neighborhood would have gotten the loan and everyone here didn't. So the overestimate turns out to be because geolocation, which is which neighborhood you're in, mediates a correlation between race and income, which is used in the actual decision variable. So the other source of variation comes from a variation within neighborhoods. And so here we have a very similar setup. So basically, let's assume the worst case where everyone in the favored group gets the loan, nobody in the disfavored group gets the loan, but they also live in this high and low income neighborhoods. So what happens in this situation? If you compute now the disparity, you would now see an underestimate, because the true disparity here is actually as bad as it could be, that everybody in the majority group got the loan, nobody in the disfavored group got the loan, but the estimated disparity is now smaller because of the imputation rule that we've used. And you can trace this source of underestimation to the misclassification error of the proxy imputation case. So basically, if you look at this tiny little confusion matrix at the bottom of the slide, you'll basically see that the difference between the true and estimated disparity is exactly that of the false negative and false positive errors due to misclassification. So I will spare you the details unless anyone's interested to look at them. But just to say that this actual mediation of outcomes in terms of mortgages and race is actually real, and you can see this in what is called the Home Mortgage Disclosure Act dataset. And this is an example that we provide in the paper. Right, so I'll just skip this unless people want to look at all the gory details. We'll come back to that later. And then the other thing I wanted to share was an ICML paper that was published by my former intern, Jun-Sik King, at Carnegie Mellon. All right, so we're looking here at fairness and fairness performance trade-offs in this paper. So this is perhaps one of the most famous articles in algorithmic unfairness and AI bias that has been published in recent history. So in 2016, a nonprofit journalism organization called ProPublica wrote an article on bias in recidivism prediction. This was, I believe, Broward County in Florida, and this is the main data point that they gave that was controversial, which was this particular judicial system was using a proprietary vendor algorithm to predict whether or not a defendant would recidivate, which is basically commit the crime again in the future, or whether or not they wouldn't. And what it turned out to be a problem is that if you are white, you were more likely to be labeled lower risk, but actually reoffend. As opposed to black, you're more likely to be classified higher risk, even if you don't reoffend. So this is basically saying something about misclassification error. And so if you actually compute the confusion matrices for the black and white subgroups, you actually get now these various conditional probabilities. And so the way we would describe the controversy here in a more modern language is that there are actually multiple notions of fairness at play here. And this model is actually fair with respect to one of them, but not another one. So so there's a notion of demographic parity, which is basically saying that the true positives are the same, regardless of what subgroup you are. And so this model clearly approximately satisfies this, this notion of fairness. However, if you look at equal false positive rate fairness to say that the model makes false predictions equally with respect to both white and black, this is not the case. You can see that the conditional probabilities that are relevant here differ by a factor of 2. There are many notions of group fairness, and I will spare you again all the details. We have some of this in our paper, but there are also many review articles here that I will point you to talk about the various notions of fairness that come up in practice. Now, the interesting thing here that we started to dig into is that when you talk about this kind of fairness, which is called group fairness, looking at the high level conditional probabilities, they basically have a common grammar. So they have a grammar that is a conditional probability, and each of these statements basically involves either the outcome variable, the predicted outcome variable, or the protected class. And these have to do with basically misclassification or classification equality. Perhaps the most famous result in this field is known as these impossibility theorems. While it's normally called impossibility theorem in the singular, there are actually two very similar but distinct results that were written by two different groups of authors. And so instead of so let me just say that the first group of authors considered basically the regression problem, where the output of the model is a risk score that you then threshold to get the actual decision. And the second group of authors looked at just the discrete classification problem. But given that distinction, they actually have the same result. So basically, here are three different notions of fairness that are expressed in terms of these conditional probabilities and conditional expectations. So basically, there is no such model that satisfies all three notions of fairness at the same time, except for very trivial circumstances. For example, a model that always says yes or always says no. So here are the two major results here. And we were interested in whether or not we could actually generalize these results to more groups of fairnesses. So one of the observations we made is that regardless of whether you're working with a conditional probability or a conditional expectation, these are actually all functions or constraints over entries of confusion matrices. So if you now write down the stack of confusion matrices for the different groups, just as we saw a couple of slides ago, this gives us basically a three-dimensional tensor, which is the fundamental combinatorial object that we look at. And now you can start asking questions about whether or not there exists such an object that is a valid set of confusion matrices, and also whether or not they satisfy the notions of fairness that you care about. So if you write this out in terms of the constraints of fairness and also the fact that these should sum up to valid confusion matrices, you basically have a linear program that describes whether or not there exists a confusion tensor that has the properties that we want in terms of fairness and also being a valid tensor. So therefore, what we've shown is that the theory of linear programs actually gives us immediately results that have to do with the compatibility or impossibility of fairnesses. And this also gives you, furthermore, a programmatic way to search over multiple sets of fairnesses to see if they're compatible or not. So these are some of the many generalizations that we were able to find of the existing work. And some of the interesting things is that if you look at the subsets here, some of these seem to come up for free. So if you look at, for example, on the second to last line and the last line, so there's calibration fairness, which is CG, equal false omission rate and equalized odds. This is one set of incompatible fairnesses, but then you see that also you can also throw in class balance, which is PCB and NCB, and that's also a notion of fairness that you satisfy for free. So there's something I don't fully understand here, but it's the main point here is to show that you can programmatically search over multiple notions of fairness to see if they're compatible. And also a simple generalization of this result also gives you notions of approximate solutions and also give you some idea of how you can do approximate trade-offs between fairness and accuracy. So basically thinking of approximate solutions to the linear program rather than exact solutions immediately gives you a very intuitive generalization of the exact impossibilities to what is actually, to basically relax it to what is actually feasible in practice. So some other related work that I've been working on in this space is also looking at cryptographically secure computation of these fairness metrics. So suppose in the first paper, we basically asked the question of like, is it possible to run the statistical test for unfairness when they don't have permissions to see the data, but let's say somebody else does. And we describe a protocol using secure multi-party computation where you can actually run calculations that would be necessary to determine compliance. And the second one here, I actually do have time, so maybe I put this in the appendix, but I'll maybe go through this a bit, which is that we have a very counterintuitive result about the ability to actually remediate fairness in practice. So I'm going to skip ahead to, first of all, what does it mean to debias a classifier? So if you have an unfair model, how could you fix it? And so the literature has basically classified bias treatments, which I call debiasing here, into these three groups: pre-processing, in-processing, and post-processing. So I don't know if there are any people who are fans of category theory in the audience, but this is the kind of thing that I went down a rabbit hole for. But if you want to talk about the differences between them, it's basically saying pre-processing is to treat the data before we train a model. In-processing is enforce the fairness during model training. And post-processing is to alter the results of the prediction so that the results are fair. Right? So regardless of the actual choice of the biasing treatment that you work on, the same general phenomenon occurs, which we're trying to illustrate here. So each point on this graph represents a pair of models before and after a debiasing treatment. And so what we're seeing here is the ratio of change of accuracy on the x-axis and the ratio of fairness changes on the y-axis. And so if you look at the black crosshairs, this represents where the ideal classifier would sit in terms of perfectly fair and perfectly accurate. So what we've done here is basically trained a whole slew of related models that differ only in the test train split that we've used for the data. And what you see here is this very unexpected result that if you think about it from a naive point of view, if I have a treatment that claims to improve fairness, excuse me, what you expect is that the fairness ratio you would get should increase from 1, so basically above this horizontal line over here, and it shouldn't change accuracy very much, or maybe it might get worse because of some implicit trade-off. So what we would expect naively is that most of these points should end up in the top left corner of this graph. But instead, the opposite is true. This basically can be all over the place, literally. So we have this counterintuitive result that trying to improve fairness can actually worsen it. And it's worsening in a very specific way. So not only can the fairness metric get worse after treatment, but the actual variance in the fairness itself increases after treatment as well. We have a theoretical result to show that this is the consequence of bias variance trade-off. So I'll skip this in favor of having a more open discussion if anyone's interested. And here's another set of results that we did. The previous ones, we were doing some fairly simple things on random forests and the adult data set. This one is a more extensive evaluation of multiple debiasing treatments as a function of multiple deep learning models that have already been pre-trained. So what we basically did was look at pre-trained deep learning models and ask, so each model is a column in these graphs, and each debiasing treatment is a different row in these two graphs. And what we see here is a general trend that confirms what we have seen. So the debiasing treatments in general improve the average fairness, which is what you're seeing on the left. Excuse me. So blue is an improvement, and orange is a worsening of the mean fairness. So you see that for the most part, the debiasing methods actually do improve the mean fairness. However, it comes at the cost of increasing the variance of the fairness metric. Once you start controlling for cross-validation and test train split and general things that we care about for measuring generalization error. And so you see that in the worst case, some of these things can actually both worsen in terms of the mean fairness and then the expected variance in the fairness metric as well. So this brings us to the point of saying we're really not in any capacity to recommend a robust and easily generalizable treatment to improve models that are unfair. That's basically where we are at this point. And this is the kind of work that keeps me occupied, and I think this is hugely interesting in the firm. So I'll just leave this as, if you're interested, we do have open positions. I'm happy to talk to you about that. And I'll just leave it here for questions. Thank you so much for having me.
Yeah, thank you, Jiahao, for a great talk. Yeah, that take questions. So if you want to ask a question, please raise your hand and I will mute you to let you ask a question. Yeah, so maybe I can go first with the question. So in one of your slides, you mentioned that in order to ensure the fairness in the output of the model, there are 3 ways to enforce this fairness constraint. So pre-processing, in-processing, and post-processing. So I wonder, because from the practical perspective, I think this post-processing is more useful because, for example, think about those natural language processing models. People spend a lot of time and dollars training those models, and they probably don't want to retrain because each run of training may cost millions of dollars. So in that sense, post-processing will be super helpful if you can make a unfair model or a model without a fairness guarantee to be a model with fairness guarantee. So I wonder if you can comment more on this post-processing approach. Is there any, for example, particular approach that you think we should read, or do you think this is what I'm saying is not appropriate
Sure.
about this 3? Yeah.
Sure. So let me walk through what my notation is trying to explain here. So X is a set of features that you want to build a predictive model from. and S is the sensitive demographics, so things like race, gender, and age. And what you do here is first you build a classifier that gives you a prediction, which is y hat. And then what you do is now build the Cartesian product of predictions for that customer alongside the demographics of that customer. And then post-processing basically is a projection back down into the outcome space, which is the green blob here. But in general, the place you end up being projected down to is not going to be the same as the starting point. So that's heuristic. That's basically at a high level what I'm trying to show in this diagram. Now, there is a problem here because if you recall the definition of disparate treatment, it's illegal to make any decision based on the explicit membership of a class. So at least under current fair lending laws, we don't think that post-processing is going to be legal, because you basically say, build a classifier that is oblivious of race, then suddenly you treat race explicitly in how you alter the results of the model. So at least under
so you're
current,
saying that S is containing X. So S is a part of X.
I've written them as disjoint here.
Oh, okay.
So assume the case where the sensitive features are not used in the predictive model, right? Because if S and X were not disjoint, then you would be also in violation of disparate treatment. However, the fact that you have to use the sensitive labels S in order to do the post-processing is the problematic part. So it's basically the fact that you start from y hat here, and you basically have to join it with S and then run the purple arrow of post-processing down here. So the fact that you basically have to first build this cross Cartesian product space is the legally questionable step at this point.
I see. So then, according to what you are saying, it looks like the second approach in processing is also illegal according to current policy, because the output y hat prime also depend on both protected attributes and unprotected attributes.
Right. So this is again, I would say this is up for debate whether or not this falls afoul of fair lending laws. So what we can say is that under our understanding of what disparate treatment constitutes right now, any explicit decisioning based on a prohibited basis is not legal. But however, you could argue that the use of these methods is meant to address the spirit of the law, if not the letter of the law. So one of the problems here is that the law is almost 50 years old at this point. And so this was written back in the era when doing any sort of statistical analysis was new. And this actually brings me to a point that the government regulators are actually currently in the process of seeking public comment on how these fair lending laws should be modernized.
I see. Yeah, but according to the illustration of these three approaches, I think the pre-processing one is probably the most legal one, right? Because
yeah, I think that's it. I think to me that's also what I would think personally. So I can't comment on behalf of like what we the company think, but I think personally this seems to be the most promising approach in terms of in terms of actually being compliant and also being able to treat unfairness.
Okay, I see. And also, I think if you just generate a new predictors X prime, and then you build a machine learning model on top of X prime, I think that also resolves the computational concern which I raised at the beginning, because you don't need to train the model twice, right?
Right. And so yeah, so in processing has the potential to be the most expensive of the three, because the enforcement of the fairness criterion happens not in the space of the data, but in the space of the functions.
I see.
So the classifier function family itself is the thing you scan over. And so if it's expensive to train and estimate a function, then you have to pay that price as you search over the function family that you're interested in.
Okay, I see. That makes sense. Yeah. Thank you. Yeah. More questions from the audience? Any other question? If you have question, please raise your hand, or you can just write your question in Q&A. All right. Yeah, looks like there's no more questions. If later you have questions, please do follow up with Dr. Chen. And yeah, so let's thank Jiahao again for the great talk. Yeah, thank you, Jiahao.
Thank you so much for having me. It was very nice to meet everyone virtually. And please feel free to reach out if you have any further questions at this point. Thank you.
Thank you.